Okay, we're gonna start about now. So again, the content is typically, rather, interesting. Of course, at various points, you can see that, in general, they are pretty, simple in every step, but because we have been developing everything from the beginning, so eventually we're gonna end up with something really interesting. So, um, do ask me if there are concerns or there are some points that you feel like disconnected from others, and I'm happy to sort of provide further thoughts and discussion about those. And in particular, there was a question on PSA that I'm not sure what, how to answer that. It was something that, that we haven't discussed, but I'm going to try to discuss it now. Also, that when I posted the post lecture notes for the previous lecture, I also explained a little bit, of how to think further. So also look into that. So I mean, so let me start a quick discussion about that first. So the first question that I received was like, so I mean, like, so an example of many solutions to the equation of h of x du equals to c. This is the sort of fixed constant energy level, right? Constant energy level. And the problem is it's being considered in the torus. Okay, so I'm just gonna write this one. So this is a fair question, and surely it's our main object for a long time to go. I haven't really given you a lot of examples because it's sort of like it takes a while to really get there. But again, it's a very fair question, and I guess that I should give you some first sort of first simple but important examples. So the first sometimes I'm touching this and it's running away. So the first remark here, if you look at this equation, is that if u is a solution, then u plus c is also a solution. It's another solution for any big constant c in R, right? Because again, there is no zero order term u here. So when there's no zero order term, if you make the function differ by a constant, you differentiate, that constant goes away, right? So naturally you have already a family of solutions that you add up to a constant. So that's the first remark. So this means that at least we should have a family of solution solutions, say u plus c for c in R. Okay, given that we have on the first hand one solution. So the second remark here is that, again, I mean, um, that again, this is a general equations, and pointing out examples could be hard. So I would focus on uh, a more explicit one. So explicit one. So let's consider, we are in any dimensions. I consider the Hamiltonian h of x and p to be p dot with p minus dc of x, okay, for some given function c, uh, in C1 of the torus or something like that. Well, okay. Um, so it's a very simple example, and this is actually corresponding to something called magnetic Hamiltonian, actually. So it has some physical meaning, but let's just focus on this, okay? Just Hamiltonian, and then I let c equals to 0, so that's the energy level I'm considering. Then the equations becomes the PD becomes that I have, like du dot with du minus dc equals 0 in the torus. Again, the energy level C is let to be 0. So, again, here you can easily guess that there are at least two solutions, right? So at least u equals to constant C1 is a solution for any constant C1, right? Because if you let equals to a constant, then du equals 0. So that's dot product with anything is going to be 0. Okay. So that's the first obvious choice. The other obvious choice is that you're going to make the second term here becomes 0. So, you can take u equals C plus any constant C2 is another solution, right? Okay, so at least you see already that in this very natural, simple example, we have at least two family of solutions. So, like C1 or C plus C2. Later on, we're going to see more that they are going to be even more. You can sort of like combine these two solution in a weird way. Well, not weird, but taking the minimum of two, if you know this already. We're going to prove later on that this is also a solution. So there's a very complicated dynamics of solutions here, and characterize all solutions and understanding everything is going to be a big deal. Okay, so that's that. The second point, so the second point that I want to explain quickly, we're going to go back. We're going to go back today anyhow, is that when I have the Hamilton Jacobi equation h of x du x equal to c in the torus with u is a C1 solution. Okay, so if u is C1, and then we claimed last time was that the graph gamma tilde equals to x dph of x dux is invariant under the Lagrangian flow, Lagrangian flow, so phi TL. Okay, so there was a question by your peers that I mean, like, why wouldn't you consider the minimizing problem first? So I mean, if you consider this problem, right, you can say that you start with a point x naught v naught, where you have x naught is given in the torus, and v naught is nothing but dph of x du x naught. So those are the two initial data for us to start the Lagrangian flow, right? The problem is that we don't know yet, I mean, what's going to be other endpoints for us to consider the minimizing problem. So I mean, what's going to be the other endpoint? I mean, how to run the ODE is questionable, right? And that's why what's this endpoint for us to consider the minimizing problem. So that's why we got to consider, so we need to consider the ODE that I wrote down last time. So gamma prime of t equals to dph of gamma t du gamma t, and gamma 0 equals to x0. So you need to consider, I mean, we need to consider this ODE on the first hand, so that we know the other endpoint, which is going to be gamma t, gamma prime of t, right? So if we know the two endpoints, and we can say that by the mechanism we developed last time, that we have that, for any curve in the between. So actually we're going to recall this today in different aspect. For any curve, we can prove that gamma is a minimizer. So for this, we don't have the global uniqueness existence theory. We can only use the Peano or Cauchy-Peano theorem to have the existence of gamma. Okay, but once you have existence of gamma, you deduce that gamma is a minimizer. Okay, as I noticed, once you have gamma is a minimizer, then you deduce that gamma satisfies the Euler-Lagrange equations, and that helps us to conclude that it's exactly going in the Lagrangian flow. And when you have really that if gamma satisfies the Euler-Lagrange equation, what is really important here is that you have uniqueness of, of gamma. Because once you satisfy the Euler-Lagrange equation, right, then you have uniqueness, because Euler-Lagrange equation here tells us that you have d over dt of dvl of gamma dot equals to dxl of gamma dot, and you have initial data gamma 0 equals to x naught, gamma prime of 0 equals to v naught, and this is enough for us to have uniqueness. But uniqueness here is of the Euler-Lagrange equation, right? So it's a very interesting way to go sort of like around and use certain things. So feel free to ask me more questions if there's something unclear. What is really a tricky point here is only one thing, is that when we use the piano theorem for existence, there we don't have that gamma as unique. Okay. But then because we use the fact that it's, it's a minimizer satisfying the Euler-Lagrange equations, then we have uniqueness of gamma later on. Okay. So I hope that that's clear. Ask me more if you have more questions or concerns. All right. So if not, then let's go back to the lectures, to the notes today. And in the meanwhile, we're gonna also explain what I have talked about, and you can also ask me more if you have more concerns. So this was already in the previous notes. It's about calibrated curve. We just define it. So you're given u is a continuous function, I is a given interval, and then for any continuous piecewise C1 curve gamma, we say that it's ULC calibrated, so ULC calibrated if essentially, okay, maybe I can draw a picture here. So you have it's an interval in I, so this is the calibrated curve gamma. So it is calibrated if you go from any like gamma. So it goes like this. You go from any gamma t to gamma t prime. Okay, so if you take any sub piece of the curve, so just going from gamma t to gamma t prime, then you see that the value on the left hand side, the difference of the u, equals to the action function on gamma. Again, c is the normalized constant, but I mean it's calibrated in the sense that it's connecting the points in the curve in the sort of optimal way, right? Because the difference in terms of value of u equals to the action function acting on gamma. Again, c is the normalized constant. Okay. And it's a very simple but also very important remark is that once you have a calibrated curve, then it's calibrated in any subinterval. In other words, it is optimal. Once it's optimal in a big interval, then it's optimal on any smaller interval, right? That's it just comes from the definitions, but that's important to remember. So if gamma is ULC calibrated, then gamma is calibrated on any subinterval I prime of I. Okay. And it's already evident from the definition, right? So let me draw again the second example. You have this curve, whatever. So gamma is calibrated on this big interval. Say here's the I. So if you take a smaller subinterval or whatever it is, I mean this smaller piece of gamma. So this is gamma restricted to I prime. Okay. So you have the smaller piece, which is a red piece. It's part of the I, right? So if you take any point here, gamma t prime here, then surely going from gamma t to gamma t prime here, is part of I, and then just by the definition here, right? You have that the difference of u acting on gamma equals to the action function on gamma. Okay, right? So that's that. right? So one of the important piece is that I recall the theorem here. I mean, this was also what we did last time, but I mean, it's important to recall it. So we say that if U is dominated by L plus C, I'll recall to you what does it mean. And if gamma is ULC calibrated, then we can deduce that gamma is CK, and actually gamma is a minimizer. Okay. And let me recall the definition here. So U is dominated by L plus C, meaning that for any curve, say eta in AC absolutely continuous from AB to the torus, or you can say C1, same, doesn't matter. Then you have that U of gamma eta B minus U of eta A is gonna be less than the action function of eta, the C of B minus I. Okay, so it's dominated by L plus C, right? So it just means that the value of U acting on the endpoints of the curve is dominated by the action function of L plus C. Okay, that's just that. So on the one hand, you can see the proof is already from the statement, right? Because you know um, so you have that for any curve eta, any arbitrary absolutely continuous curve eta, then the action functional of L plus C of eta is always greater than the endpoints, right? But on the other hand, because gamma is calibrated, so the action functional of gamma equals to U evaluated at the two endpoints, right? So clearly from that you imply that gamma is a minimizer, right? And then you're done. Okay. So again, you see that it's sort of the same game. So let me put the two boxes here. So what I just said for eta as this one, for general eta, you have the red box down here. And for gamma, it's a minimizer. I'm sorry, it's a calibrated first. So I have this red box here. So, on the top red box here, I have equality because gamma is calibrated. On the second red box, I have inequality because this is for arbitrary eta, right? So then you can combine the two boxes here to deduce that gamma is a minimizer, right? So you have gamma is a minimizer of this action functional. And again, you have to fix the two endpoint. And this also comes back to you see questions in others question earlier, right? You got to know the two endpoints in order to confirm that you have a minimizer, right? Because if you don't know both of the endpoints, and it's not clear, what are we minimizing over, right? So I fix the two endpoint, gamma A, gamma B first, and then I consider any eta in the between. I mean any other eta. Then it just show us that gamma is a minimizer, right? So gamma is ck because that's what we have used 10 first lectures to prove it. Okay, so you see that you know now that we can really enjoy a lot of things that given to us beforehand, right? So that's good. um, so just to summarize, so just to sum up, you're gonna use this property a lot, that U dominated by L plus C just shows that this is a property that holds for any curve eta. Okay, and gamma mapping from I to the torus is calibrated, is ULC calibrated. Then this one essentially implies that okay, so gamma is a minimizer of the action functional I with fixed endpoints determined by gamma. So gamma A, gamma B. Okay, so I want to emphasize this point because because sometimes in this context, we actually going to encounter this a lot later on, is that when you consider array or something like that, when we don't have the fixed endpoints, then we have to be careful. So we got to have fixed endpoints in order to consider the minimizing problem. Okay. All right. So any concerns or question up to this point? Anything? No? Okay. Now again, do ask me if you have questions. I'm always happy to share, what's in my mind with you, because this class also, I mean, I really enjoyed it, but also it takes me lots of time to make the viewpoint systematic, because Fatih's book is good for the taste of dynamical system people. I'm trying to sort of make a harmony transition between dynamical system and PD, because I want to introduce to you both viewpoints. It might be a little bit sometimes I might forget something, although it's in my mind, but sometimes I might not writing it down clearly. So do ask me if there's something unclear. Okay. So now the next one is about another important result. This is about characterization of C1 solution. That's the next point that we are mentioning, right? The second point of the lecture today is about characterizations of C1 solutions. Okay, so C1 solution, again, our main object is still h of x du equals to c in the torus. That's the main object, and we want to see, I mean, how do we characterize solution to this equation? Again, given the things are in C1. So let's see. Yeah, so the first claim is just what I just said. No big deal here. Okay. Second claim is about that, U is bounded, is dominated by L plus C. And for each of the point X, we can find epsilon greater than 0 and a C1 curve gamma that is calibrated and going through the point X. Okay, so this is rather a remarkable point. What it says that on the first hand, so this is I, that is equivalent to 2I. So 2I is remarkable in the sense that U is dominated by L plus C. This says nothing about a solution to a PD, right? Just saying that U evaluated at the two endpoints is less than equals to any action functional. And then what is also remarkable is that what it says is that if you fix any point X in the torus, we can find just a local curve passing through it. I mean, this is the geometric meaning of that. So gamma is a calibrated. Okay, I'm lazy, so I'm not gonna write ULC, but I'm just saying it's calibrated. Curve passing through it, so I have gamma 0 equals to X. Okay, so it's very geometric, right? Because on the one hand, we are talking about solution to a PD. On the other hand, we are talking about curves. And then what it tells remarkably is just that, we can find a tiny curve, for very local, right? Just from minus epsilon to epsilon that passing through that point. Okay. Okay. Again, here we need to assume that it's C1, so I should emphasize that. All right. And then the third one and the fourth one are actually weaker than the second one. Third one and fourth one are only saying that, it's dominated by L plus C, and you can find a curve, but starting from 0, either going from 0 epsilon with gamma 0 equals to X, or minus epsilon 0 with gamma 0 equals to X. So they are weaker, right? So I should say that, I mean, okay, let me try to draw a picture. So maybe 3i is enough. So this is should be equivalent to 3i, which is about that u is dominated by L plus C, and then you have a calibrated curve for sure. So this is x in the torus, but your calibrated curve is only going halfway. Okay, so this is gamma 0, and your gamma is calibrated. Okay, so is they're remarkably interesting, and again, this is actually one of the very important points in the whole course, because we are talking about dynamics of the curves, and then what's going to be interesting uh, is that here for any point there's a small local calibrated curve passing through that point if your solution is C1. Okay, later on we're going to talk also about this, and then there are lots of hidden things here. But for now, I just want to mention that sort of the statement, nothing more than that. Okay, so let's see. I mean, so I mean, so our strategy, how we're gonna do things, right? I mean, of course, you can see already in the proof, and you have read the proof supposedly. But the strategy is that we're gonna show that, because we need to show the three things are equivalent. So we're gonna show that I implies 2i. This is rather clear because actually we have done that last time, but let me recall it anyway. We have done it. It's not easy, but again, it took us sometimes already. So I'm gonna show that 2i's implies 3i's. This is obvious actually. Right? I mean, we don't need to show it at all, right? We just look at the diagram, right? Because I require the calibrated curve to pass through x. So x is in the middle, right? And 3i is weaker. It's just about, you know, a tiny piece, but with the beginning point x. So it's already, you know, this one already implies this one, right? Okay, so that's not hard. And then we're gonna prove that either, okay, maybe I should say this one implies 3i or 4i. So, and you know, one of the two, it's fine, you can use one of the two, and then we're gonna go from 3i or 4i's back to I. Okay, so that's the strategy. Okay, and when we are doing that, I'm gonna also give you comments about things. So uh first thing first, let's look at the proof. Okay, so I believe we already proved that if U is a C1 solution, then U is dominated by L plus C. That's we already proved. But if you need a quick proof, then you can just recall it, right? I mean, this proof we already proved it, but you can just recall U of eta B minus U of eta I, because U is C1, so this is A to B du eta S dot with eta dot of S ds. Again, is fundamental theorem of calculus, and then the trick same and same all the times is by the inequality. So h of eta S du of eta S plus L eta S eta dot of S ds. And then remember that h of eta du of eta equals to C. So we are done for that part of proving that U is dominated by L plus C, right? And now the second part is, you know, I just mentioned it, and we have proved it, right? Because we say that du is continuous, and then dpx of du is continuous as well. And then by Cauchy-Peano theorem, you know, Cauchy or Peano theorem, depending on context, then you have short time existence of the ODE. So you can define this ODE for short time, right? And again, I recall that we don't have uniqueness here because we don't have, it's known to be Lipschitz, right? Of course, here you can ask me a question. So let me make a quick remark here about this point. So remark. I already said it out loud, right? But I want to make sure that we mention this point. Is that in fact here, remember that in the uses of the Cauchy piano or piano theorems, then you have your ODs defined for a short time and epsilon depending on the boundedness of the vector field. In this case, the vector field is bounded and you are in the periodic domain, so everything is compact and nice. So in fact, you can define it from the interval from minus epsilon to epsilon and then epsilon to 3 epsilon, and you keep defining further and further. So in fact here, we can use the piano's theorem inductively, whatever, to have that gamma is defined in the whole R, right? Such that you have gamma dot of t equals to dph gamma du of gamma and gamma 0 equals to x. Okay, so I mean it's always like that, and then we already proved it last time that this gamma is a minimizer, right? And it satisfies exactly the equality. When I wrote it up here, I have this inequality, but if you choose gamma dot to be exactly dp, then you have equality. So we are done. Okay, any question or concern here? Is it clear? Maybe let me just write it down. And because of this choice, you do have the equality, right? I mean, we keep repeating it, but it's good to write du gamma s dot with gamma dot of s equals h of gamma s du of gamma s plus L of gamma s gamma dot of s. Okay, that is important because of our choice, and that was the reasoning that we were using last time, right? I mean, I was telling you that we can just do it in an ad hoc way, but if you look back into the proof, then we need to make the equality happens, and that gives us this choice of the ODE. Okay, so that's good. We are done for this, and then remember this part. Okay, I'm gonna come back to this at the end of this lecture. Remember that gamma can be defined for the whole real line. Okay, and as I said, going from I to 3i or 4i is obvious. It's just 3i and 4i are more restrictive. We are only requiring a calibrated curve starting from gamma, starting from x. So it just half of the line segment, not the whole. I mean 0 to epsilon or minus epsilon to 0. Okay, so finally we're going to show that 4i's implies I. Okay, so what's 4i? Let's record. I'm going to draw a picture here. So this is 4i, right? That you have u is dominated by L plus C, and you have a calibrated curve just going from epsilon minus epsilon to 0 with gamma 0 equals to x. Okay, so let me also draw a supporting figure here. So we are proving that 4i implies I. So again, we have u is dominated by L plus C, and we have that for any point x, which is gamma 0, we can find a calibrated curve. This is gamma minus epsilon going to gamma 0 equals to x, and gamma is calibrated. Okay, so your calibrated curve gonna end with x for any given x. Okay, so it's clear what to do, right? Because you know what to do. We are just writing it down like what we have. So you know, gamma is this gamma that we drew the picture on the right, and then you have the equality, right? So just write out the equality. So you know, we are saying that you can start from minus epsilon to 0. So that means that you can start from any point like gamma minus t to 0 for for any epsilon no 0 less than t less than epsilon, we can just go from gamma minus t to gamma 0, right? So if you go from gamma minus t to gamma 0, you have the left hand side, this one, the difference in values of u equals to the action functional on the right, which is this one, okay, on the right. And now we know what to do, right? Because typically in analysis or in anything, that when you know how to put it, uh, when you can vary the parameters, and you know, you either varies the parameter to certain values that of your interest to, or to infinity or to 0, because whenever we want to see the derivatives, it's a natural way to let the parameters vanishes, right? So that you can see the infinitesimal changes, right? So that's a natural way. So if I can vary the t, then I'm just gonna let t goes to 0 anyway, right? Just to see the derivatives, right? That's a natural way to vary the parameters. So yeah, so we do that. So I take the left hand side divided by t equals to right hand side divided by t, and then we let t goes to 0. You know, um, when you do that, the by chain rule, the left hand side just gives you that dux dot with gamma dot of 0, right? So that's the left hand side. Because what we are doing is that, so this is x equals to gamma 0. When you do the measuring the infinitesimal changes, then what we are measuring is that when you let t goes to 0, then it's going to give you the gradient in this direction, right? So this is gamma dot no, I'm sorry, going, this is gamma dot of 0, right? Just measuring the change in this tangent direction to the curve at 0, natural, right? Okay. And on the right, again, it's just a natural way to use the chain. No, you are just using the mean value theorem, right? So this is equals to L of gamma s, gamma dot of s plus c for some s between minus t to 0, and then when you let t goes to 0, this one just converge to gamma s converge to x, right? Gamma dot of s converge to gamma dot of 0, again assuming that gamma is nice, right? Because we know that it's ck, remember, right? Any calibrated curve is ck. Okay, so you converge to the right hand side, which is L of x gamma dot of 0 plus c. Okay, so this is the right hand side. So yes, it's good that we have seen the first derivative of u coming out, right? And this is a first order equation. It's beautiful. It's already there. So you're just switching the L to the left. So you have dux dot with gamma dot of 0 plus L of x gamma dot of 0 is less than equal to c. Hold on, equals to c. I'm sorry, not less than. And by definition of the Hamiltonian, right, this is, recall that h of x dux equals to supremum of all v dux dot with v minus L of xv. So the top one is going to be less than equals to the bottom one, right? Because the bottom one is supremum all over all vector v. So we concluded that h of x dux is greater or equal to c, okay? And remember that earlier when we have that, if U is C1 and dominated by L plus C, then you have already the sub-solution property. So H of X du is less than or equal to C. So combining the two together, you have the conclusion. So that's it. Okay. So you have here the super solution property. Up here is the sub-solution property. So from the two, you concluded that H of X dux is equal to C. Okay. Yeah, so I could say that it's rather remarkable because the second or the third or the fourth property is only talking about U being dominated by a function, and then about the fact that through any points you can find a calibrated curve, either ending there or starting there, or I mean having that point in the middle, whatever. But that leads us to the following definition of Wickham solution. So there are two definitions. So it's either of negative type or positive type. So either negative type or positive type. So in our class, so in our class, we will typically only deal with Wickham solution of negative type. Okay, why? Because they are essentially the same, not the same, but I mean they are similar, and I don't want you to feel confused with too many notions. So I'm gonna stick with one, and I have decided. So I've thought about this a lot. Actually, preparing for each of the lecture is really interesting, but also you know taking time to decide what to do and what to go further, what to sort of like leave it as it is. So I'm gonna just focus on the negative type. So I'm gonna draw a picture of what we are meaning here, and this is actually a big object, because you remember that the title of our course is named Wickham theory, right? So this is sort of one is our main object. Okay, so we're gonna mainly focus on this. um, um, so S minus is the set of all such solution. And U is in S minus if, it's Wickham solution of negative type, if you have that U is dominated by L plus C. Okay. So let me highlight it. So dominated by L plus C. And then the second point, which is really interesting, is that we say for any point X in the torus, we can find a ULC calibrated C1 curve going from minus infinity to 0, that having gamma 0 equals to X. Okay, so geometrically, we are saying that for any X in the torus, we can find a calibrated curve, gamma from minus infinity 0 to the torus with gamma 0 equals to X. So it's a ray, right? So it's a ray ending or starting, whatever you mean here. So X is in the torus. And then you can find a ray going from minus infinity to the torus. No ending point, right? It's keep going on forever. So this is gamma. Okay, so that's our backward our calibrated curves, and it's negative type simply that we going to minus infinity. Okay, so positive type is just that going from 0 to infinity. So the two going to be the same. That's why I'm only focusing on one. And in the literature, in the PD literature, sometimes So this gamma, again, in Wickham theory, Fatty name it calibrated curve, or maybe not Fatty, some others as well. Curve going from minus infinity to 0, right, to the torus. In PD language, we name it backward characteristic. Starting or ending, whatever. So ending, okay, ending at x. So you go from minus infinity to somewhere and you end at x. So this is a remarkable thing to start with, because we are only dealing with the fact that the definition is that we only require that u is continuous, right? So u is just a continuous function, and we say that this is a weak KM solution if it satisfies the two properties, again dominated by L plus C, and you can find a backward characteristic, or a calibrated curves going from minus infinity to 0 and ending at the point x. Okay? So clearly we're going to try to characterize all possible weak KM solution and really connect the dots with the PD language and various things. You might wonder like what I'm doing here, so let me give you two remarks before we end. Remarks. The first thing is gamma is going from minus infinity to 0 to the torus. It's calibrated with gamma 0 equals to x. Okay. So far, actually, we haven't talked yet really about modern dynamical viewpoint. We are having just talking about, as I said, minimizers of from finite interval to the torus and stuff like that. And we have done a lot of preparations, but not yet anything about deep dynamical properties. So you have this gamma here, right? So later on, we're going to talk about, like asymptotic behavior, as I said, of gamma. So gamma, I can also think of it as a curve from minus infinity 0 to Rn. I can lift everything to Rn. Then people often going to ask about the question, what's the behavior of gamma t over t as t goes to minus infinity? Does it converge to anything? So this is the so-called rotation vector. If there's such a rotation vector, then does it converge to anything? And then people are going to also talk about the ergodic behavior of gamma, right? Because you can imagine that, you can think about it as a curve in the torus, or you can think about this is gamma 0 equals to x. Is your curve periodic, or is it sort of dense in the torus, or does it gives you some invariant measures out there, right? Because it wraps around the torus, and does it give you certain invariant measures and stuff like that? Okay, just a heads up, saying that we're gonna dig deep into this one. That's rather remarkable. Okay. So those are that, and then the second point is that you might wondering is that S minus is the set of weak KM solution of negative type. Again, this is nothing negative, it's just that we are going from minus infinity, so we call it negative type. So we only require that U is continuous, right? So you see that we have thrown away the differentiability of U, and that's remarkable. And so note that actually we have already proved it's hidden in the proof. If okay, let me change it to V. V is in C1 of the torus, and h of x dv equals to C, then automatically V is in S minus. Okay, so that's the other point that I want to make sure that we are on the same page. If it's a C1 solution, is automatically in the set of Wickham solution of negative type, right? Why? If you go back to this remark, is here. It's here. Right? Because if V or U is C1, then you can just define your curve gamma in the whole real line, right? So so if V is like this, then you can just define gamma prime of t equals to, or dot of t equals to dph of gamma t dv of gamma t, and gamma 0 equals to x. So you can actually this is the point x, and you can define your curve gamma going from even minus infinity to infinity crossing through x, and this is and this gamma is surely calibrated. That's what we have proved. Okay, so you have automatically a a curve from R to Tn that satisfies this property and is calibrated. So that means that if you have C1 solution, then automatically, I'm sorry, that you have that is a Wickham solution of negative type. But what we have defined gonna contain more, right? It's gonna contain some other hidden solutions that need not to be C1. Okay, right. So I think that I'm done for now. I have time for some quick questions if you have any. Any concerns or anything you want to discuss?
Is there any relation between extremal curves and calibrated curves?
Calibrated curve, so okay, so when we have defined it here, right? So this is the result that we proved, right? So if U is bounded or dominated by L plus C, and if gamma is calibrated, then it's a minimizer, right? So it's stronger than an extremal curve, right? So surely it's an extremal curve. It's a minimizer, right? Okay. Yeah, because when we define it to be extremal, then that it just means that it's a critical point, and minimizers surely extremal curves, and sure, um, and there are names in this field that make you feel confused. So calibrated or extremal and stuff like that. But here, um, in order for calibrated curves to be minimizers, then you need to have also that U is dominated by L plus C. That's why. So you need the two. Okay? But other than that, then sure, they are linked together.
Thank you.
Yep. Okay.
So I have a question. So with this definition, you don't need to prove existence of minimizer and still is able to find some sort of desired curve.
Yes. Yes. Yeah, you're right, because this definition, it's rather abstract, right? It just tells us that, hey, I mean, I'm so lucky that I can find a sort of a calibrated, and because that is dominated by L plus C, so I can find a minimizing curve going from minus infinity 0 to the torus. So hidden here is sort of a big question, like how can you find such a calibrated curve, right? So that's a fair question, and then we need to discuss about this. But at least I have verified to you a simple thing is that, okay, if you have a C1 solution to the Hamilton-Jacobi equations, and sure, it's a Wickham solution of negative type, right? Um, and we have to use the piano theorem and use the ODE to show that there's a calibrated or minimizing curve. So that's really a fair question. And again, I mean, it's an abstract theory. So when I throw at you this definition, um, you know, I remember some of my friends, back in the day of grad school, they was telling me, I mean, what's the thing with Wickham theory? It looks so abstract, and what? But it turns out it's quite neat. Eventually, we will be able to characterize all such Wickham solutions. Also, I'm gonna give you a very quick PD characterization of that. It's gonna take us lectures to do so, but you know, if V is in S minus, if and only if V is Lipschitz and solve this equation in the box in the viscosity Y. That's all. We're gonna prove that. Okay, so bear with me, but we're gonna get there by the end of the class. Hopefully.
I have another question. Is there an algorithm to find these things?
Sure, of course. You mean find the curve or find V?
So you to find both, right? You have to have some sort of sub-solution V and then some random curve, say that is dominated. And from there, can you cook up an algorithm that leads to a fixed point?
Yes, so we're gonna do certain fixed point theorem actually to find Wickham solutions of negative type. That's gonna be our goal, and there are certain numerical algorithms to find V. So this is a big deal actually. Up to this moment, there are a lot of works trying to find V in a better ways. Um, so it's a very active research direction. Um, I'm also trying to think about that as well. That I can say, and it's not easy, but it's doable for V. Now, finding gamma, I know some of my friends. I mean, there's a professor like in Japan. Kohei, I mean, he's working on finding gamma, but up to now, I'm not aware of a very efficient way to find gamma, and understanding it ergodic behavior, because that's really hard. So yeah, but I mean, this is really important. I mean, it's finding gamma is a big deal. Yeah, but
Thank you.
yeah. So you see that we are already touching research here. I mean, we are touching things that are yeah, but I can say some things with confidence because I've thought about that. Something then I might not be able to answer you. Okay. All right. So that's great. Thanks a lot for the interactions and the questions. I love them as always. Because this is topic course. I mean, it's supposed to be so with lots of discussions and stuff like that. So see you on Friday then. I'll try to post the next lecture notes in a timely manner. Right? So see you. Thank you.